All right. So, good morning, everyone. This is Shivkant Tilekar. I'm Senior Application Engineer of SolidWorks. And this presentation will be about how we can improve our heat exchanger designs using SolidWorks Flow Simulation. And I hope you're all excited about it. So let's start and go forward with it. So if I talk about some key facts about the SolidWorks, here they are. SolidWorks is a worldwide offices of 23, and as you can see in the graph, the customer put their explicit trust into the SolidWorks. It is clearly presented by the graph. And so is it true about Beacon. Beacon is a reseller of the SolidWorks, and we have a headquarters in Bangalore, and we have 8 offices across the country, including Pune. So as you can see, there are huge customer database that we have, including the small, medium, and large industries. Moving on to our current agenda, then as you can see it on the screen, SolidWorks provides you the intuitive solutions for your day-to-day simulation work. Not only the finite element analysis, but also with the flow simulation as well. Not only that, and plastics here can also be one of the solutions from the SolidWorks. So here's the brief of my agenda that I'm going to present it. First, we're going to explore what is a fluid flow analysis and why we are investing in it, our time, our money, why we are investing in it. And secondly, why SolidWorks Flow Simulation? What's the biggest thing about SolidWorks Flow Simulation? What we do is we'll take a real life examples of SolidWorks Flow Simulation. We're going to include the industry specific modules, and I'll show you a demonstration on the SolidWorks itself, and then we summarize our session. So this is very brief agenda for this today's session. All right. So if I talk about what is fluid flow analysis, if I simply put it, fluid flow analysis of simulation, it's a simulation of the real life fluid and heat transfer problem on a computer, and it converts these real life problems into equations and solve them numerically using the power of computers. I remember from my childhood that we used to play with this floppy disk, which fits on the size of my hand, which was carrying the 5 MB data only. But today, computers have evolved so much so that we can make use of those evolved power to solve some real life problems that we are facing day to day. In this case, we are going to solve our real life problem of heat exchangers. And who can benefit from it? The answer to this question is very interesting. The engineers designing the products, that those can benefit from it. They can immerse into this environment and simulate the problems that you're facing beforehand. They can greatly benefit from this. And of course, if the designer succeeds, organization will thrive. So why SolidWorks Flow Simulation? It will help you to improve your efficiency and the performance of the product. It will help you to innovate. It will help you to improve the quality of the product. And of course, the other parameters too. It can reduce down the cost. It can reduce down the weight. And it will ensure your safety and reliability of the product, which will gain the confidence in the customers. That's the biggest thing that you'll get using the SolidWorks Flow Simulation. Otherwise, if you do not use, then for validating the product, you have to do such a kind of rigorous testings, which involves a lot of costs. As you can see, this is one of the typical example of the heat transfer lab, where you can see the heat exchanger has been placed over here, and the rigorous testing has been carried out. You have to assign a space, you have to assign a qualified person, and then carry out the test and match the results and move on. But with the SolidWorks simulation, it can give you the faster leading time and the less expensive cost, in the less expensive scenario. Of course, it will give you the comprehensive results that you can evaluate, and it required very less efforts and manpower for this. So why follow SOLIDWORKS Flow Simulation? The answer is right away in front of you. It will give you the single window integration with the SOLIDWORKS. As you're already using the SOLIDWORKS, it is a great tool to add in and evaluate a product right into your user interface itself. You have a power of 3D model with you. You can make use of that 3D model and get on with the more accurate evaluation of the products using the SOLIDWORKS Flow Simulation. It is very easy to use, and it is having very short learning curve. And of course, if I compare with the other products, it is very cost-effective product that you will get. So if I talk about some technical capabilities of the SOLIDWORKS Flow Simulation, here are some. We have 3 modules in the SOLIDWORKS Flow Simulation. First one is flow simulation itself, where we solve the problems of these kind, like internal and external analysis, heat transfer problems, time dependent problem, conjugate heat transfer problems, and all. We do have a separate package for the electronic cooling. In electronic cooling, we solve a problem like joule heating, and we have extended database of thousands of materials that is required into the electronic cooling scenarios. Of course, we have heat pipes. We can solve the problems for the heat pipes. And for the HVAC, we have that module also, where we can do the advanced radiation study and study the comfort parameters for the HVAC. So coming on to the SOLIDWORKS Flow Simulation, I list down some of the technical capabilities of the flow simulation. Here, we can solve the problems for the incompressible or compressible flows, viscous flows also, and supersonic also. We can play with the different types of fluids, such as Newtonian and non-Newtonian fluids, and we can specify any conjugate heat transfer problem that we are facing, or the radiation problems, and we can do the time dependence fluid flow analysis as well. And of course, you can know that the mathematics behind us, it solves the Navier-Stokes equation, which is the formulation of the momentum and energy conservation law. Here you can see the Navier-Stokes equation is basically follows the Newton's second law. Here is a term. This term can be put it as a mass into the acceleration. The pressure forces, it's a summation of the forces over here. It's basically solved the Newton's second law. And not only that, it can solve not in the laminar problem, but also the turbulent flow problem here as well. With the standard module of K epsilon, it can solve the turbulence problem. You can directly enter the values of the turbulence parameters right into the user interface of it, and we can solve. And it can also solve the conjugate heat transfer problems using the variety of equations and joule heating problems here as well. And the mathematics inside, we do have the white papers for you, and if you're interested, we can explore more on this horizon. So here I'm taking a very real life example for the SOLIDWORKS Flow Simulation and the product demonstration. Here the objective is very simple. For this demonstration, I am taking the plate heat exchangers, and here are the aim of this aim of this study is to calculate the rise in the coolant temperature. Coolant will be entered from this side and will exit from this side. The rise in the coolant temperature we want to check, and we want to check the temperature distribution in the one of the plates over here. The refrigerant that I'm going to use is R123, and the boundary conditions has been specified over here, like it will flow at the inlet of 0.01 kg per second. The coolant temperature while entering here is -5 degrees Celsius, and the outlet will be at the environmental condition. Here, the air is a secondary fluid, and in that the temperature of the air is 25 degrees Celsius, and it will flow in the x direction. The x direction is this one. As I will go into the SOLIDWORKS interface, I'll elaborate more on that. So air will flow at 40 meter per second. So we want to check the rise in the coolant temperature as the air flows through the CD exchanger, and we want to check the temperature distribution of the plate. So this is a very simple objective with which we can determine, okay, is this really a good heat exchanger for this, and we will conclude at the last. So if I go and simply enter into the flow simulation model setup, I encounter first thing is the flow project wizard. So where we can enter the project name and the configurations that we are currently using over here. Once these values are entered, we can define the unit system of our choice, and these unit system can be customized according to our standards or industry. Along with that, we can specify the type of analysis over here. The external analysis is like the fluid flows over the solid boundaries, and the internal analysis is so fluid flow inside the solid boundaries. This is a very general description that I'm giving to you. So we can specify the other parameters also. If you want to do any time dependent study, we just have to check this parameter. Along with that, we can specify the gravity, rotation, as well as the free surfaces. Not only that, if we just move on, and we can define the fluids that is the part of the study. We have a very extensive fluid library. We just have to click over here and specify any fluid characteristics. If you want to add any fluids also, we can add this using this interface. And afterwards, we have to specify what are the solid materials involved into this analysis. And of course, afterwards, we can take care of the wall conditions, roughness, type of wall. Is there any adiabatic wall, or is there any heat transfer through the wall? We can specify the thermal conductivity and all using this interface. And finally, we can specify the initial project conditions using this setup. All right, so I'll just move on to the SOLIDWORKS interface and show you live. As you can already see, I have this 3D CAD model ready with you. Believe me, 3D CAD model is a very powerful asset that you have, with which you can take an advantage of the various simulation parameters right into your CAD interface. So for this SOLIDWORKS simulation, you just have to turn on this flow simulation add-in from the flow simulation tab, or you can directly right away go into the add-ins and turn on the flow simulation right away over here. Once this is turned on, the new tab will appear, and we have the extensive commands to specify any real-life conditions for the flow simulation purposes. I already gone ahead and specified some of the conditions that I specified. For you, we are just checking the widgets. The widget will appear like this one, and we can go on specifying the parameters that we are of interest. Once it is specified, we can check in the boxes and specify the parameters. For this project, I have already specified one of the descriptions. As you can see, I just have to activate that project. Once it is activated, I can move on to specifying the general settings for it, and it will be an external type of analysis, and heat conduction solid and it's turned on because there are some there will be a heat conduction between this copper plate, copper tubes, and this aluminum plate that is there. And I already specified the solid types accordingly. The default solid is an aluminum, and other solids will be specified from this interface, and this will treat it accordingly. The fluids, as I already told you, is specified as R123 real gaseous fluid, and air will be the secondary fluid in this case. And the initial conditions is like the air is at 25 degrees Celsius and it will flow in the X direction. As you can see, the X direction is like this one. It will flow in this X direction. So once the initial condition has been set up, we have to go and use this interface right away over here. As you can see, the interface is very intuitive. We can directly specify the different types of materials. The boundary conditions is very easy to specify over here. And if I just go here and insert the boundary conditions, I can directly specify different types of boundary conditions. As you can see, there are a variety of boundary conditions depending on the flow openings, pressure openings, as well as the real world boundary conditions. If you want to enter any thermodynamic parameters, these can be entered right away over here. along with the turbulence parameters to capture the real the fluid phenomenon directly into the CSO interface. Once these things are specified, we can, if there are any heat source, we can specify any heat source. But in this analysis, there isn't any heat source. The objective is different. So we can go ahead and track our goals right away using this goal tab. In the goals, we can insert different types of goals. We can insert global goals, surface goal, and volume goal, depending on the requirement. Here I have entered those goals. And if I just talk about the meshings, there are two types of meshing is already available over here. First one is a global mesh, and second one is a local mesh. So if I just view this meshing using this interface, as you can see, there are different types of mesh which is already available. If I just show this mesh, as you can see, it will capture the solid elements as well as the fluid elements in a greater details if we just go ahead with the local mesh. In the presentation, we'll compare the global mesh versus local mesh. We'll elaborate more on that upfront. Okay. The meshing is very important parameter over here because it will transfer the mathematical fluid conditions from one cell to another cell, and so on. It will do the calculations upfront. So once these things have been specified, we just have to solve the project over here. So if I just run the project over here, we have extensive observer run as well as the batch run. And once this thing have been shown, I can, with the help of the cut plots, I can explore more on the temperature of the end plate, temperature of the solid, as well as the temperature of the the temperature of the refrigerant as coolant over here, and what happened to that. So let's move on to the presentation and see it. So as I was saying, there's a difference between the global mesh refinement versus local mesh refinement. And local mesh refinement, as you can see it in here, we can capture the small features into the greater depth. The same model have been shown over here, but here the less fluid element has been captured, but in the second model, the more fluid element captured, which gives us basically the better mesh refinement and good results. So SolidWorks uses the advanced immersed boundary condition meshing technology here as well. So with the help of this adaptive meshing, we can capture the very critical mesh areas where the fluid flows are unpredictable. We can capture these flow areas with the help of adaptive mesh refinements. So if I just compare the immersed boundary Cartesian mesh, which is used in the SolidWorks versus other CFD software, which uses the body fitted grid generation, the results are right in front of you. It will give you the efficiently, it will efficiently mesh your model, and it minimizes your errors, and it will minimize also the local and truncation errors over here. And it will, of course, make the grid generation robust and flexible using the immersed boundary condition mesh which SolidWorks uses. So if I just go ahead and show about the results, here are the results plots that are over there. The temperature of the coolant is raised from -5 degrees Celsius to 20 degrees Celsius. So the environmental temperature was 25 degrees Celsius, and here we are actually rising the temperature of the coolant from -5 to 20 degrees Celsius. So let's take a look at the temperature of the solids from the end plate. So if I just probe the results, you can see it into the screen. The temperature distributions in the solid is right in front of you. The temperature of the solid rises gradually from the 16 degrees Celsius. This is the cut plot for the end plate. The cut plot for the first plate will be different. I just consider the end plate over here. For this end plate, the temperature of the solid here is around 17 degrees Celsius, and then it will gradually rise to Celsius, as you can see. And if I just talk about the conclusion, the temperature distribution is not that much uniform in this case. And this idea I can get into just by using the flow simulation software right away into the design feed itself. We don't have to manufacture the product to actually see what will happen. So this is the power that you get using the flow simulation. So if I just talk any temperature changes of the fluid, as you already seen, the environmental is at around 25 degrees Celsius. And if I just take a cut plot around the right plane of the cross section, and as you can see, this is a pipe. And if I gradually probe it, as you can see, the temperature of the coolant or the refrigerant, it will rise gradually from -5 degrees Celsius from here, or say 0.7 degrees Celsius from here, to 19 degrees Celsius, around that much. Hence, we can take a better design decisions early in the design processes. So what will happen if I don't use the CFD? As you can see it in this graph, if I use the CFD downstream to put out the fires, our efforts is much more while we just use the CFD upfront. That means if I use the CFD in early stages, I can considerably reduce down my efforts. That's the biggest thing about this sort of flow simulation. I have a second examples to discuss with you. This is about the shell and tube heat exchanger. There are a variety of heat exchangers we can solve using SOLIDWORKS Flow Simulation. For this presentation, I have just chosen the plate heat exchanger as well as the shell and tube heat exchanger. And in order to solve this study, my objective is to check the fall in the temperature of the hot water in the shell and tube heat exchanger. And my objective is also to calculate the efficiency of it. And the boundary conditions are as follow. As you can see, the hot water will inlet at 0.0002 meter cube per second, and outlet will be at environmental pressure from here. And it is from the tube side, and from the shell side, I have the cold water, which is at 50. The water. In the previous study, we have seen two different types of fluids. Here, I'm only talking about the water, hot water, and the cold water. Fluid is essentially the same. And if I just go ahead and talk about the temperature distribution of the solid, here is the graph. As you can see, the fluid, the hot water over here is at the 90 degrees Celsius, and the temperature of the fluid where the cold water enters, it dropped significantly. Of course, this will show me, yes, which is a real phenomenon, right? So if I just go here and show the same thing into the SOLIDWORKS interface, and tube heat exchangers have been prepared for this. If you just want to go here and transparent, make it transparent. Once these things are transparent, we can easily see through the product that I have. And if I just turn on any cut plots that I already shown it to you, I have a power to probe it here right away. At the entry, the temperature distribution is 90 degrees Celsius, and as it get very close to the cold water entrance, this is an parallel flow heat exchanger, so the entrance will be essentially on the same side. The temperature distribution here is temperature will fall from 90 degrees Celsius to almost 61 degrees Celsius. And for the exit of the cold water will enter from 15 degrees Celsius, and it will exit almost at 29 or 30 degrees Celsius over here. There's a 15 degrees Celsius rise. And here also, from the hot water, it will decrease the temperature from 90 degrees to 64 degrees. So these things is essentially have been captured in this bowl here as well. So if I just hide these plots and delete these legends, I can basically go for the cut plots and show you the results right away over here. And you can take an extensive measures and extensive values over here. As you can see, the average temperature of the hot water inlet is at 90 degrees Celsius almost, and the outlet it will around 68 degrees Celsius. So fall of this is almost of 30 degrees. And along this the cold water will enter at 15 and rises at almost 15 degrees Celsius rise. So if I can go ahead and specify any equation goal here as well, so that I can make use of those parameters and calculate any equations such as the efficiency over here. And of course we can plot any flow trajectories. With the help of this flow trajectories, we'll have the idea about what's actually going on into our system. Here the flow will enter at 90 degrees Celsius, as you've already seen, and depending on this legends, you can see with the help of color flow trajectories what's the situation of the flow. So it is definitely an alternative development process for our day-to-day engineering work, where the design validation part start after the design. With the help of SOLIDWORKS, you can start this design validation process right before your product design here itself, right along with the product design itself. So it will typically replace the serial process with the parallel process, and we can make a better design decisions early in the stage. So in the summary, I would like to summarize this as a design validation. We can do it early in the stage. Of course, it is integrated with the SOLIDWORKS, and it will answer what if scenarios extensively right away. And it is a single source of solutions. And if I just talk about the training and support, you're all aware of the Beacon support. Beacon gives a very extensive support for the flow simulation as well as the other products of the SOLIDWORKS as well. The flow simulations in the heat exchangers. It can also be extended the same capability of the computational fluid dynamics to solve the problem of the electronic cooling as well as the HVAC room, the wall performance, the board performance, etc. So typically, it is a fully integrated platform that SOLIDWORKS offers. It's not only limited to the CAD modules. It can also have the simulation along integrated with this design validation part. It will offer the inspection solutions as well, and for the rendering purposes and all other purposes and the technical documentation purposes, it will offer the composer. And in order to view the SOLIDWORKS file and the results file, we can make use of the e-drawings here as well. So if I just talk about industry verticals, the figures are right in front of you, and these solutions have been accepted by the global market leaders as well as the inter-market leaders over here. So with this, I just conclude my session, and if you have any doubts, you have this window to get this out clear. Please ask.